Hey guys, welcome back to the lab. Today we're going to be talking about dextromethorphan, a common over-the-counter antitussive medication. Antitussive meaning used therapeutically to suppress coughs, commonly referred to as cough syrup. So just to give a quick history of dextromethorphan, the parent compound of DXM, racemethorphan, was discovered by a pharmaceutical company called Hoffmann La Roche. And they filed patents for that parent compound in the late 40s. And then eventually, in the early 50s, dextromethorphan, the dextrorotary enantiomer of racemethorphan, which I'll get into more later, what that means exactly, was first isolated. In the early 50s, after DXM was first isolated, it was tested by the CIA as a part of Operation MK Pilot on Navy personnel as a potential alternative to codeine as an antitussive. Of course, codeine has a lot of issues that come with it in terms of addiction potential, abuse potential, and all that. They were looking for something with less abuse potential and negative effects. Eventually, in the late 50s, DXM was granted FDA approval and began seeing circulation as an over-the-counter preparation in the United States. Eventually, it became known for being abused recreationally for its dissociative hallucinogenic effects. In the 70s, a brand known as Romular was taken off the shelves due to a massive increase in purchases attributed to recreational usage. So since the 70s, there's been attention on the substance. During the 90s, there was a bit of an explosive increase in recreational use due to the ability to disseminate information over the internet. Since the 90s, it's been on and off the feds and media's radar as a substance of concern. So in this video, we're going to do a brief overview, mostly from the perspective of pharmacology. But before we get into the pharmacology, I'd first like to get into the chemistry of the substituted morphinans, the structural class that DXM belongs to, because I think it's pretty interesting and it's pretty relevant as a whole. So I'll just go on and get right into that. All right, so first of all, DXM is a substituted morphinan. That means that it contains the morphinan structure with certain additions to it. Primarily, morphinans are opioids, but in certain cases, they will have much reduced affinity for the opioid receptors. I'll go more into why later. So here in the middle, we have racemethorphan, which is a racemic mixture of two enantiomers. In chemistry, an enantiomer is a molecule that has chirality, that is that it can have different spatial orientations. So as you can see, these two molecules are mirror images of each other. If you put them on top of each other, it wouldn't be the same. If this were flipped. That has to do with the 3D conformation of the molecule. That is, with this nitrogen heterocycle here, it's in this view, the thicker lines indicate that it's coming out towards you. So if you flip this, the nitrogen will be going away from you. And if you tried to superimpose that over this, it wouldn't match up. So they're called stereoisomers or enantiomers in this case. So a racemic mixture is generally a 50-50 combination of both enantiomers. And those enantiomers are labeled either levorotary or dextrorotary, depending on their orientation. In the case of racemethorphan, we have its two enantiomers being levomethorphan and dextromethorphan. Levomethorphan being the levorotary enantiomer of racemethorphan, and dextromethorphan being the dextrorotary enantiomer of racemethorphan. It's also indicated by a minus or a plus, sometimes, or D or L. So if these molecules are so similar, why do they have such drastically different effects? Levomethorphan is a prototypical opioid. That is, it primarily acts on the opioid receptors in the brain, while dextromethorphan is a dissociative hallucinogen, therapeutically an antitussive, but it exhibits a much more diverse binding profile. It targets many more sites. And this is a good example of how such a small change in, not even a change in the actual atoms in the molecule, but a change in its spatial orientation, how the molecules are arranged in space. And that small change can be enough to drastically affect the ability for the molecule to interact with certain receptors. If you think of a receptor as containing people use like puzzle pieces as a comparison. I don't think it's a very apt comparison generally, but right now it kind of makes sense. The receptor has sites on it, and depending on the molecule's shape and its conformation and its constituents, it can have less or more affinity to that site. And in the case of the mu opioid receptor, as small of a change as the spatial orientation of the nitrogen heterocycle can be the difference between, in the case of levomethorphan, extremely high affinity, and in the case of dextromethorphan, very low affinity. Not negligible affinity, it still has affinity for the mu opioid receptor, but drastically reduced in comparison to the levorotary isomer. And that all is a consequence of the ability for these molecules to interact with those receptors. All right, so I just corrected a mistake. I accidentally wrote hydroxy here instead of methoxy. But if you look at the 3 position on the structure of the morphinan group, 3 position on the race methorphan enantiomers has a substituted methoxy group. That is, it has an oxygen bound at the 3 position carbon with a methyl group attached to it as well. And that's the same on both of these. This is still the 3 position in terms of naming conventions. And then it also has the nitrogen group methylated. Over here it's not methylated. On the race methorphan molecules it is. So race methorphan is the general name given to it, but it could also be called 3-methoxy and methylmorphinan. So over here I drew morphine just as a comparison. So with morphine, you can see it has hydroxyl groups on the 3 and the 6 position of the morphinan structure, and as well it has a pretty distinctive bridge between the 4 and 5 carbon positions, which forms a sort of heterocyclic ring, as well as that the nitrogen is methylated. So generally, in terms of substituted morphinans, dextrorotary isomers or enantiomers of the corresponding racemic compounds will be less active at the opioid receptors, while the levorotary enantiomers will be much more active there. And not all of the substituted morphinans are optically active, meaning not all of them display optical isomerism. Certain ones do, certain ones don't. It depends on the molecule, but in the case of race methorphan, it does. So yeah, I'm going to move on to the pharmacokinetics of dextromethorphan, because I feel like before we discuss the dynamics, and kinetics is how the body affects the drug, and dynamics is how the drug affects the body. DXM has active metabolites, and that's important for how its effect profile manifests. So I wanted to get into the kinetics before the dynamics, and just discuss how the body processes dextromethorphan before it reaches the brain. So when DXM is ingested, there are 2 primary enzymes that are responsible for its hepatic metabolism. That is, these are liver liver-produced enzymes. Part of the CYP 450 group of enzymes, cytochrome P450, and they are CYP2D6 and CYP3A4. So the metabolic pathway of DXM looks something like this. So you have DXM, unaltered, unmetabolized dextromethorphan. It can be affected by these two enzymes in different ways. That is, the molecule itself can be altered. So through CYP3A4, you see conversion of dextromethorphan into a compound called 3-methoxymorphanan, or 3-mem, and that's due to the demethylation, the removal of a methyl group at the nitrogen. Here, I'll just illustrate DXM. This is a bit of a poor illustration here, but so this is DXM, the original unmetabolized molecule. When you have 3A4, the CYP3A4 enzyme, demethylated at the nitrogen, you see a removal of this methyl group. Like that, which is 3-methoxymorphanan. It still has the 3-methoxy group here, but the nitrogen is demethylated. So another route would be through CYP2D6, and that would form a compound known as DXO, or dextromethorphan. Dextromethorphan is the product of O-demethylation, that is, demethylation at the oxygen. Another name for dextromethorphan is 3-hydroxy N-methylmorphanan. So once these changes occur, and not all of the DXM is metabolized, it depends on a lot of factors. There's a significant deviation in genetic expression of especially CYP2D6 enzymes within the population. So some people have more than baseline, some people have less than baseline, and that will affect how the ratios of conversion into these metabolites. But after the first metabolic change, the enzyme that corresponds to what didn't originally metabolize it, so in the case of 2D6, 3A4, in the case of 3A4, 2D6 will convert a smaller portion into 3-hydroxymorphanan, which is the product of both N and O demethylation, that is, demethylation at the oxygen and the nitrogen. And then after this, eventually they'll be conjugated into excretable metabolites that can be removed through the urine. But these are the primary hepatic changes that occur prior to DXM's and its metabolites absorption into the bloodstream and movement into the brain. So not much is known about 3-methoxymorphanan in terms of affinity for receptors and all that, but dextromethorphan has been significantly studied and is thought to be the primary mediator of recreational doses dissociative effects. And recreational doses can be many times larger than that of a therapeutic dose. Another thing that I'd like to mention that's related to the kinetics of DXM is the different forms it may take. There's three primary ones. There's dextromethorphan hydrobromide, which is the salt of dextromethorphan and hydrobromic acid. Then we have dextromethorphan freebase, which is kind of implied by just the DXM by itself. I'll just specify free base. And what that means is when you have compounds that contain a nitrogen group, a lot of different alkaloids and other substances, a lot of times when they're not conjugated with an acid group, that is, they're not reacted with like hydrobromic acid to produce the hydrobromide salt, when they're in this free form, they're considered a free base because the nitrogen contributes to a very weak degree of basicity. So the third form is DXM polistirex. This one is interesting because there's not a whole lot of information regarding polistirex online. When I first looked into it, it was kind of referred to as a polymer, like just a plastic-like polymer that somehow delayed the absorption of DXM. Now that's partially true, but I did some digging into patent information regarding the patents regarding compounds that are used in polystirex, which is a composition of multiple elements. So polistirex itself is a sulfonated polystyrene compound, and it essentially acts as something called an ion exchange resin. What that means is that in certain conditions, it will exchange ions for other ions. So in the case of DXM, if you have, I'm not going to draw the whole polymer compound. So you have the polystirex. It contains a sulfonate group, and that group contains an oxygen that is negatively charged. And dextromethorphan contains a nitrogen that is able to ionically bond with that oxygen. And the polystirex is a polymer, so it's composed of many monomers that are available as a substrate for the dextromethorphan to bind to. According to the patents that I read, if this is taken directly, like without anything else, just pure DXM polystirex, the extremely ion-rich environment of the stomach, which is acidic, and that means that there's a lot of free protons, essentially, more or less, to oversimplify it. There's a lot of free protons in solution in the stomach due to the stomach acid. So if you just take DXM polystirex, it will mostly just immediately dump the DXM into the stomach because it has a more favorable ion, that is the proton, the hydrogen ion, which it can conjugate with. And that's more energetically favorable for the polystirex molecule, so that results in the ion exchange where DXM is released and the proton is conjugated with the polystirex. So what they do is they use these things called coatings, and DXM polystirex formulations are generally liquids, so it's not a coating in the sense of like a pill coating where it's a solid. They use like certain, usually non-polar compounds such as like vegetable oil or oily substances like that. They use it like on a molecular level to coat this resin, this ion exchange resin, and DXM conjugate. So it coats it in this like layer of lipophilic material, and there are degrees to which it can be coated depending on the formulation. So that's what actually prevents it from immediately being dumped into the stomach. It acts as an enteric coating, which means that it delays the release of most of the drug. It delays that until it reaches the small intestines, because the coating acts as a physical barrier that prevents ion interaction with the exchange resin and then consequent exchange of DXM with a different ion. Long story short, polystirex is an extended release formulation of DXM. All right, so I think that kind of wraps it up in terms of kinetics. And so I guess now I can get into the dynamics. Now, dynamics, like I said, is how the drug affects the body, and the body includes the brain. Many people seem to conceptually separate the two, but the brain is part of the body. I'm mostly going to be focusing on the brain side of things here, but DXM has a lot of peripheral effects as well, like on the heart, and mostly in larger doses on the heart and in the lungs, and its activity as an antitussive cough suppressant. DXM and DXO, that is dextromethorphan and dextrofan, or 3-hydroxy and methylmorphanan. And they carry very distinct effects, especially in terms of recreational use. It's more relevant to recreational use because many of the targets that these two substances have affinity for, they have very low affinity and a very diverse range of targets. So when taken therapeutically, they don't really display a clinically relevant effect at a lot of receptors, but when taken recreationally, that is at doses that are many times that of the established therapeutic dose, it will begin to accumulate at those receptors to a significant degree. So, like I said earlier, dextrofan is primarily responsible for dissociative effects, and that has to do with their binding profiles, the targets they bind to and their affinity for doing so, the ability to bind to those targets. So in general, the primary activity of dextromethorphan is that of a sigma receptor 1 agonist, which has 142 to about 652 nanomolar dissociation constant, Ki value. And the higher the Ki, the less affinity it has for a receptor. So like having 1 Ki means that the drug is much more conducive to binding at a receptor than if it had 100 Ki. And it also acts as a serotonin transporter blocker and a norepinephrine transporter blocker. So in that sense, it has SNRI capabilities, serotonin norepinephrine reuptake inhibitor capabilities. DXO's primary targets are the NMDA receptors, by which they act as an uncompetitive antagonist, which I'll go more into in depth in a bit after outlining their targets. They also act as sigma-1 agonists with less affinity than dextromethorphan, but still significant affinity, especially at recreational doses. And dextrofan also is active at the mu opioid receptors. It has very low affinity for the other opioid receptor subtypes, that is the kappa and delta opioid receptors. But at the mu opioid receptors, at which it acts as an agonist, it has a Ki value of about 420 nanomolar. So having like 400 nanomolar isn't usually that significant. But when you're taking a drug at multiple times the concentration that is recommended therapeutically, it starts to become relevant clinically in terms of effects. And then also DXO has effects as a blocker at the serotonin transporter and the norepinephrine transporter, although it has less affinity than dextromethorphan at those receptors. Dextromethorphan has a Ki value at serotonin transporters at about 23 to 40 nanomolar, and its affinity at the norepinephrine transporters is 240, which is, especially at the serotonin transporters, is a relatively high affinity compared to the other receptors that it targets. And then dextrofan at serotonin transporters has a Ki value of about 400 nanomolar. Much less affinity than DXM at that site, but still not negligible affinity. And then it has about 340 Ki at the norepinephrine transporter, which is close to the value of dextromethorphan at that receptor. Dextromethorphan and its metabolites are considered dirty drugs, which is kind of a broad term. That means that they target many different sites. For example, both DXM and DXO also target the dopamine transporters, the serotonin 1A and 2A receptors, the beta adrenergic receptors, the dopamine receptors, the histamine receptors, the muscarinic acetylcholine receptors, and also to a much lesser degree the nicotinic acetylcholine receptors. I'm sure at high doses that these receptors also play a role in the effect profile of the drug, but it's unclear as to the degree of which each receptor plays a role in that effect profile. So these are the ones I'm mostly focusing on, just because it has a higher affinity for these. So just to explain how it affects each one of these targets, and what that means for its effect profile. With sigma-1 agonism, the sigma receptors are poorly understood generally. It's not clear what endogenous ligand binds to these receptors, but it seems to be that they're implicated in cardiovascular function, depression, schizophrenia, and bipolar and cancer. And they appear to modulate calcium release and also modulate cardiac myocyte contractility, as well as voltage-gated potassium channels. Now, all that being said, it's poorly understood how these mechanisms that they seem to be implicated in actually translate to a physiological response. So it's inconclusive as to how the sigma-1 receptors play a role in the effects of dextromethorphan and dextromethorphan in terms of recreational effect profile. Now, what we understand a lot better than the sigma receptors is the serotonin and norepinephrine transporters. These are monoamine transporters that help facilitate reuptake of endogenous monoamines. So you have a presynaptic neuron, an action potential is fired down the corresponding presynaptic axon. There are vesicles within this neuron that contain neurotransmitters, often monoamines, including serotonin, norepinephrine, dopamine. So when a signal is propagated, it can stimulate the release of these neurotransmitters from the presynaptic vesicles into the synaptic cleft here. And the synaptic cleft allows for a space for these neurotransmitters to be released into, and then correspondingly bind to sites on the postsynaptic neuron. Eventually, the monoamines will dissociate from these receptors after binding to them and eliciting a response. Eventually, they'll dissociate, and then the transporters, the monoamine transporters, help facilitate the movement of these monoamines back into the presynaptic neuron and back into those vesicles where they're stored to await another neuronal firing. What a monoamine transporter blocker does is it binds as an antagonist to that transporter protein and inhibits it. So it increases the time that the monoamines are in the synaptic cleft and increases the time that they are exposed to these receptors and can interact with them. SSRIs are an example of a serotonin transporter blocker. SSRI stands for selective serotonin reuptake inhibitor. The selective part meaning they're selected for serotonin transporters specifically. But reuptake inhibition is the process of antagonizing these transporter proteins so that they can't perform their baseline function and returning monoamines to the presynaptic vesicles. Long story short, the monoamine blocker activity of DXM results in higher concentrations of serotonin and norepinephrine in the synaptic clefts of relevant neurons, and it increases their time in the cleft before they can be transported back into the presynaptic cleft and the vesicles. So this presents potential for dangerous interactions. If you have a SERT blocker, a serotonin transporter blocker, it opens up the possibility of serotonin syndrome if you mix this substance with something else that is a serotonergic, whether it's a serotonin agonist or also another blocker of SERT. It potentiates the effects at that target. So for example, if you have something like ecstasy, MDMA, which is 3,4-methylene dioxymethamphetamine, that acts as a releaser of monoamines from the presynaptic neuron. It stimulates the release of monoamines from these vesicles. And if you combine that with like a SERT or NET blocker, That means that you're going to have increased release, increased concentration, and a more sustained time in the synaptic cleft of these monoamines. So that can lead to dangerous interactions, which is just something I thought I'd mention. Now on to DXO. So DXO acts, like I said, as an uncompetitive antagonist at the NMDA receptors, the N-methyl D-aspartate receptors. And what the uncompetitive part means is that it's a conditional blocker. It requires a certain condition to be met. So if you have the NMDA receptors represented like this, so normally this ion channel, the ion pore that allows ions to travel into the cell upon activation of these receptors, the pore will be closed and it won't allow the passage of ions. Now when you have glycine and glutamate bind to these receptors, it initially doesn't do much, but if you have other intracellular cation influx, like the influx of sodium and potassium through like the kainate receptors, for example, it depolarizes the membrane significantly, which displaces a zinc cation that blocks this naturally, and that causes like an explosive depolarization of the membranes. These are very excitatory receptors implicated in helping catalyze rapid depolarization and then consequent hyperpolarization of the neuron, which generates an action potential. But when the cell becomes significantly depolarized by other means, by kainate receptors, by ion pumps, whatever, you got sodium, potassium in the postsynaptic neuron, and that causes the magnesium blockade to leave. So now these receptors are open, and they're open for calcium influx. So once this condition is met, that is, glycine, glutamate are both agonizing the NMDA receptors, it's sufficiently depolarized already to allow the efflux of the magnesium blockade. Now, this is when the DXO is able to bind, because its site is within the channel pore. This is called the MK801 or PCP site. Now it's a similar site to the magnesium blockade here. It's within the channel pore, within the ion pore, so it physically blocks ions from being able to pass. And but it requires this receptor to already be open, which is why it's called an uncompetitive antagonist. A competitive antagonist would bind at one of these orthosteric ligand sites and block the orthosteric endogenous ligands from binding there. A non-competitive antagonist would bind to an allosteric site, like a separate regulatory site. Now, DXM doesn't have particularly high affinity for the NMDA receptors compared to like ketamine or something. But if someone takes a recreational dose, it's gonna be relevant then, due to the high concentration overcoming the low affinity. Essentially, if you have enough of it, even if it has low affinity, it'll be enough to elicit the effects at that receptor in a significant way. So we also have mu opioid receptor agonism, which means that DXO can bind to the mu opioid receptor, which is the primary opioid receptor implicated in the euphoric and addictive properties of opioids, like morphine, heroin, etc. And it binds there in the same way that they do as an agonist. The mu opioid receptor is a G protein coupled receptor, so it then elicits a response via secondary messenger, etc. Like I said, it doesn't have particularly high affinity for the mu opioid receptor, but at recreational doses, it could be relevant. And then also, as well as DXM, it binds to the serotonin and norepinephrine transporters, but at a much lower affinity. So it has that effect as well. That about wraps up the dynamics, the pharmacodynamics of DXM and its metabolite DXO. And now I'd like to talk a little bit about potential toxicity, that is, potential damage to neurons and to the brain as a result of DXM use. Now this topic is a bit contentious, a bit controversial, and the reason it is because there was a study done I don't remember when, by a researcher named Olney and his team. And they were investigating the potential of an NMDA antagonist toxicity, also called NAT, um, in various NMDA receptor antagonists, such as ketamine, phencyclidine, PCP, and also dextromethorphan. Now, originally people thought that dextromethorphan could potentially cause lesioning in the brain. Olney's lesions, they're called, named after the researcher, which are lesions, spots of neuronal degradation where neurons have died because of underexcitation as a result of NMDA antagonism. People originally thought, especially due to information posted on the famous DXM FAQ, which was published in, I believe, 1997 by William White, which was a definitive source of information regarding dextromethorphan for recreational users. And it was a good source for the times, but at one point he mentioned the possibility of dextromethorphan induced Olney's lesions. The thing is, in the study itself, which I've read, Olney tests large amounts of dextromethorphan intraperitoneally in male rats, that is, injected into a body cavity, usually the stomach. In those rats, at concentrations of 75 milligrams per kilogram, which is extremely high, like the highest recreational dose that you'll see is probably around 12 to 14 milligrams per kilogram. So 75 milligrams per kilogram, that's a fuck ton of DXM. And he was injecting it intraperitoneally, which is a method of administration that results in a faster absorption than orally, for example, which is the primary method of administration for recreational and therapeutic use of DXM. So that seemed to cause lesioning these male rats. But then he also gave similar doses to female rats orally and failed to replicate these results. And so that's caused a lot of controversy. I mean, there's no empirical evidence as of yet proving lesioning as a consequence of DXM abuse. However, that doesn't mean that it doesn't do that. Absence of evidence doesn't necessarily equate to the lack of a phenomenon. It could cause lesioning. I mean, other NMDA antagonists have been shown to cause a certain degree of lesioning and then subsequent atrophy, which is the death of much larger portions of neurons in the brain. This has been demonstrated specifically with chronic ketamine users who take super therapeutic doses, that is recreational doses of over a gram a day for half a year up to, like 7 years or something. And ketamine in that case was shown to induce significant atrophy in their brains. Or at least there was a correlation between heavy ketamine use and the atrophy of these people's brains. However, there's been no such studies done for dextromethorphan. And I think that there really needs to be some, because like I said in the intro, I mean, like, dextromethorphan has become very popular. I mean, not necessarily like super mainstream, but it's become more popular for recreational use. The 90s, saw a huge proliferation and dissemination of information regarding recreational use. And consequently, there's been what seems to be a steady increase of recreational users. I think it's incredibly important that someone researches the long-term effects that chronic use can have on the brain, because we don't have anything. And some people take that lack of evidence for proof that it doesn't do anything, which may not be the case. I think likely isn't the case. Personally, I think that based on what I've read and what I've seen regarding similar substances and the anecdotal experience I have being a part of communities that focus around harm reduction and the use of dextromethorphan recreationally, I would be surprised if it did not have some degree of it's inherently a dangerous drug. Everything should be done in moderation, I believe. I don't personally use dextromethorphan, but it seems that the trend is that chronic sustained heavy use is what is the common denominator in long-term effects, changes to the body, including the brain. So I'm not trying to like fearmonger here, you know. I'm a strong believer in harm reduction. I think people should have the facts and make informed decisions based off of them in terms of what they're going to choose to put in their body. You know, I mean, I think that's up to the individual, and I'm not trying to like, I'm not encouraging or discouraging use here. I'm just saying that I wish this was studied more, because when you have more information, you have more of the facts that you can present to people, and people can make more of an informed choice. And currently, there's a distinct lack of said information. All right, so I think that's all I wanted to talk about, really. This turned out to be a bit longer than I thought it would be, but I hope it was informative, and yeah, I'll talk to you guys later.